Bismillahirrahmanirrahim. Welcome to the Electrical Engineering YouTube channel. In this lecture, I am going to demonstrate the overall phasor diagram of a transformer at no load and with loaded condition. And the overall phasor diagram of the transformer consists of voltage phasor at the primary side and at the secondary side. Similarly, current phasors and flux phasors and the components of current which are flowing through the magnetization branch, etc. So first component of current is called IM, which is the magnetizing component of no load current. And in the first case, we are dealing with the practical transformer at a no load condition. And we know that whenever a transformer is operating under a no load condition, all of the current flows through the magnetization branch, which can be seen in this equivalent circuit diagram. So there is no load at the secondary side, and all this primary current is supposed to flow from this branch. And in this branch, we have a resistor in parallel with this inductor. So this resistor is only present in a practical transformer. While we are discussing an ideal transformer, there will be no such resistance. So this resistance corresponds to the heating loss of the iron core, because whenever a transformer is operating, it gets heat up. So heating loss is always represented by means of this resistor. And this current has two components. This is IW, which is I naught cos phi naught, and this is IM, which is I naught sin phi naught, and this I2 will be equal to 0. So IC is the core loss component of no load current, and IM is the magnetizing component of no load current. And I naught is equal to IM square plus IC square, and its under root. So the overall phasor diagram of the transformer can be drawn here for this particular case when we have no load and we are discussing a practical transformer. This is a phasor orientation of the primary applied voltage, and the induced voltage at the primary side will be 180-degree out of phase with this applied primary voltage. So E1 is shown in the downward direction. Similarly, E2 will be in phase with the induced voltage at the primary, and the phasor of V2 will also be in phase with this E2. And this is the flux, and we know that flux always leads the induced voltage, which we already discussed in one of our previous lectures. So flux leads the induced voltage by 90 degrees. So this is the direction of flux, and this is the current I naught. So I naught is lying at an angle phi naught with V1. So I naught is the no load current, and I naught is actually lagging behind the applied voltage V1 by this angle phi naught. So I naught has two components. One is the vertical component and one is the horizontal component. And in this case, since this is phi naught, the component in front of this angle phi naught will be the vertical component. So this component will be I naught sin phi naught, or this component will be IM, the magnetizing component. Similarly, the other component, which is this IC, is the horizontal component of this no load current, and it is equal to I naught cos phi naught. So this is a practical transformer at no load, and if we discuss the ideal transformer at no loaded condition, again this is V1. Here we will have E1 and we will have E2 also here. This is the direction of flux, and in ideal transformer there is no such resistor. So I naught will be equal to this IM, because there is no resistance, and all of the no load current will be the magnetizing component of the no load current. So I naught will be equal to I naught sin phi naught. So it means phi naught is equal to 90 degrees. So this angle is 90 degrees, and we have IM equal to I1. So this is the case of the ideal transformer, and the ideal transformer doesn't get heat up, so there will be no such resistor. And this is the practical transformer. This is the equivalent circuit of an ideal transformer, both at no loaded conditions. And now we will discuss the case of a transformer at loaded condition. So first, the ideal transformer at loaded condition will be discussed. And in ideal transformer, the Im magnetizing component of current is always in phase with the flux. So this is V1, and at the opposite we will have E1, and E2 will be in phase with E1. So for a lagging power factor load, this current I2 will be definitely lagging behind the voltage E2. So secondary current is lagging behind the secondary induced EMF by an angle of theta. And this is the primary voltage V1, and this is I1. Sorry, this is I naught, and we have to uh, this is I2, and we have to invert this I2. So I2, the inverse of I2 will be I2 dash. So this is I2 dash, which is at 180 degrees, which is lying at an angle of 180 degrees with this I2. And why we have inverted this I2 current? Since we know that the secondary current is 180 degree out of phase with the primary current in a two winding transformer, so we have to consider this I2 dash current, and this I2 dash is basically equal to minus I2. So actually I1 is equal to I naught plus I2 dash, or we can say that I1 is equal to I naught minus I2, since the secondary current is 180 degree out of phase with the primary current. So in order to add this no load current I naught with this I2 dash, we have to apply the head to tail rule. So this is I naught, this is I2 dash. So we can place this vector I2 dash over the head of this Im vector, and I1 will be equal to the vector sum of this Im and I2 dash, or Im and I naught are equal for an ideal transformer. So this is the phasor diagram of ideal transformer for a lagging power factor load. Similarly, for a unity power factor load, E2 will be in phase with I2, and here we have I2, and I2 dash will be upward, and we can place this I2 dash vector over the head of this Im vector, and we can add this Im in I2 dash using head to tail rule method. So this is the I1, the resultant vector, because I1 is equal to I naught plus I2 dash. And in the final case, we have this leading power factor load, and we have again the ideal transformer, and in this case this is E2, this is I2, and there is an angle theta between E2 and I2, and definitely I2 is leading E2 in this case. And here we will have I2 dash, and this is I naught, and I2 dash can be placed over the head of I naught vector, and the vector sum of this I naught and I2 dash is called I1. So this is the phasor diagram of transformer for a leading power factor load. Now we will discuss the practical transformer at loaded condition, and the only difference between ideal transformer and practical transformer is that I naught is equal to Im for an ideal transformer, but I naught will be slightly upward, and it will not be equal to Im. So here we will have I naught. Im is actually lying at in parallel with this flux vector. So this is I naught again for a lagging power factor load. This is the direction of I2, and this is the direction of I2 dash. We can place this I2 dash vector over the head of this I naught vector, and the vector sum of these two vectors is I1. And here we have the case of leading power factor load. So this is I2 leading the E2 voltage, and this is I2 dash, and this is I naught, and we can place this I2 dash vector over the head of this I naught vector, and their vector sum I naught plus I2 dash is the I1 vector. So this vector is I1, and again this is phi naught. Phi naught is the angle between V1 and I naught, and here we have phi 1, and phi 1 is the angle between V1 and I1. Again in this case, this current is I naught, and this angle is phi naught, and this current is I1, so this angle is phi 1. For a unity power factor load, I2 and E2 will be in phase, and this is the flux, this is I naught, and I2 dash will be upward. We can place this I2 dash vector over the head of this I naught vector, and their vector sum will be called I1. So this is phi naught the angle between V1 and I naught, and phi 1 is the angle between V1 and I1. So the that is all about the phasor overall phasor diagrams of transformer at loaded and unloaded conditions for practical and ideal transformers. I hope you have enjoyed this short tutorial. For watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.